Hi, in this video, we want to take a look at leave one out cross-validation. Okay, so remember that from our previous video, we were talking about cross-validation. What our game plan is that we break up our data into different groups, and then on one group, we pull it out and we say, this is our validation set or test set, depending on how we're going to proceed. And then the rest of the data is our training data. Then we grab a different group, we pull that out, everything else is training data. And then we grab a different group, pull that out to be validation data, everything else is training data. And so if I have k-fold cross-validation, and let's say I have five sets I pull out, everything else is training, 1, everything else is training, 2, pull it out, everything else is training, 3, pull something out, pull that set out, that's 4, pull that last set out, that becomes validation, everything else is training. Okay, that is our cross-validation. And what this does for us is we build, in that example, we build 5 models and we get 5 validation metrics from running the predictions on our model on the validation sets for each of those 5 iterations. And this is the gold standard for evaluating the quality of our model. Now, leave one out cross-validation is exactly what it sounds like. So it's k-fold cross-validation, but with a twist. That twist is whatever number of data points I have, that is the number of folds I have. Well, if you think about that for a moment, that means that each time my validation set is 1 observation. Okay, so what we do, we take the first observation, pull it out, and we take the rest and we build a model. Then we take the second observation, pull it out, we take that first observation and put it back also. And we build a model, and then we check our validation statistics. Then we put it back, we take the third observation, put it into the validation set. So now I've got the rest of it, build a model, and check the accuracy of the prediction. All right, so if I have, let's say, 100 observations, what I'm going to do, I'm going to pull an observation out 1 time and build a model off of the remaining data 100 times. Okay, so why do we like this? Well, first of all, I get a pretty, I get 100, scores for the model accuracy. So, I mean, that's pretty good. I get a lot. I get a good sense of what is the distribution of the error. When is this a good time to run? Well, if I'm only going to be running a prediction on, let's say, like 1 observation, then this is a pretty natural choice for that. And, there's something to be said about getting like a full distribution of error terms, because that gives me a feel for like a 95% confidence interval going into it. So I can get, it's bootstrap-ish. It's not actually bootstrap, but you can see that I get like an interval of error values, and I can see, what's the central tendency, how spread out is it, how likely is my error going to be highly skewed right, very big value, how likely is it to be a very small value. We have, a good amount of information, and this is something that we can really leverage. Disadvantages. The disadvantage is that this is a high computation problem. Okay, so if it takes a long time to build the model on my original data set, then it's going to take a really long time to run this all those 100 or so times. So when I have a more complicated model, let's say like a neural network, and I have a lot of predictor variables in there, a large amount of observations, and I'm running a pretty complicated neural network with lots of hidden nodes, lots of hidden layers in there. You know what? It's going to take a while to build each time for these, and then it's very computationally intensive. So I really only want to do this when I have like small data. An exception to that is multiple linear regression. Multiple linear regression actually has a special formula that, using other values that we get from regular regression, we can get leave one out cross-validation overall like error measurement for free. It just works out that way. And it's very nice. It's a pretty slick thing. I saw it when I was a graduate student studying linear regression. We're not going to talk about it here. Just know that if let's say you're going to be doing multiple linear regression, so this doesn't work for generalized linear regression, this doesn't work for logistic regression, just like vanilla linear regression. If you're in a vanilla linear regression problem, you can get leave one out cross-validation nearly for free. So, it's a good thing to pull out, take a good hard look at. It's not as popular of a metric that way as I thought it would be, when I discovered it, but yeah, whatever, people do what they're going to do. All right, so something you want to do to check to see, is this a good option for you, is first and foremost, when you run the model on your entire data set, does it take a long time to run? If it takes a long time to run, you know that leave one out cross-validation is a bad choice. All right, so one thing you could also do if you want to get a better idea, do k-fold cross-validation with a large number, let's say like 25, 30, 50, something like that. And if you find that it just takes too long to run, you know that leave one out cross-validation is going to be worse. So, if I'm in a situation where I want to do a neural network, I want to do support vector machines or random forest, something like that, what I can do is, okay, let's do cross-validation with 25. And if that's relatively fast, then I might want to go ahead and jump to leave one out cross-validation. So what I want to do, I want to take a look at the code on doing some cross-validation, leave one out cross-validation. All right, so what we're going to do, just like almost always, we're going to pull in Seaborn and Matplotlib, NumPy and Pandas. Now, once again, we're going to be using the ultimate Halloween candy power ranking data set from Kaggle. And this information is just copied and pasted straight from Kaggle. And not straight, I did modify it a little bit, but go to Kaggle. Here's the website for you. 538 is where it's posted, and you can take a look at it. All right, so what we want to do for our leave one out cross-validation, first thing we're going to do, we're going to use Pandas to read our comma-separated value data set. Then we're going to say, what are our predictors? I call that X. And then what is our Y variable? That's going to be the win percentage. All right, so remember how this data was generated was it said candy 1 or candy 2, which one's better? Candy 1, candy 2, which one's better? How frequently did it win? All right, so now let's go ahead and pull in random forest. So for this problem, we don't really care that much about the random forest regressor. We just want to be able to demonstrate how to get leave one out cross-validation. And let's go ahead and pull in, pull in mean squared error from scikit-learn. And let's go ahead and define our random forest regressor. I'm going to call it RFC. And I'm going to just go ahead and say the number of trees is 25. Why am I picking that number? To make it fast so that I'm not spending a lot of time waiting for it. Usually 50 to 500 is good. If you need more than 500 trees, you probably need to go back to an earlier phase in the data, probably data prep or data collection, experimental design, something like that. And for reproducibility, I go ahead and I set the random state. And the reason why I do that is so that later down the road, I can get the same random forest as I get today. Now, remember, if I have a different operating system, different version of Python, a different version of Spider, the random state may or may not carry over to other people's computers. So just be aware of that. There's really not much you can do about it, just being knowledgeable. All right, so we want to pull in cross-val score. And how we do leave one out cross-validation this way is what we do. We take cross-val score and we set the number of folds equal to the number of observations in our training data. Boom, we got it. Isn't that awesome? That's awesome. Now, I always like to use the mean absolute error instead of mean squared error when I'm evaluating a model. Mean squared error has a lot of nice theoretical properties when we're doing linear regression, but the interpretation is not as straightforward, you know, because I've got the squared error, then I take the average, and if I want to deal with that, I can take the root mean squared error, and it just kind of gets befuddled to try and understand what is the error, while the average absolute error rate is usually pretty easy to interpret how far off, left or right, from my predictions the actual observations were. So that's my preference. So I use it almost every single time. And I find that decision makers find it more natural than having to think about, all right, it's the square root of the sum of the square deviations divided by n. Yeah, they don't want to think like that. They want it as simple as possible. All right, so we use make score to go ahead and set it up in Python to evaluate the error the way we want. And I'm going to go ahead and say that n is equal to the number of rows as our X predictor data set. So we have 85 on there. It's not very big. And now let's go ahead and get our cross-validation results. And you'll notice, so something that really should jump out at us is that I'm setting the number of folds equal to n. So each observation gets pulled out one time. Everything else is in the training set. And then I check the accuracy on that one observation. And then I repeat, but pulling out a different observation. All right, so now let's go ahead and take a look at our cross-validation results. All right, so we can see that for all 85 observations that we've got, when I pull it out, build a model, check the accuracy on that one observation, we're going from what? See, I'm just gonna eyeball it real quick, 0.7 all the way up to 20. All right, so it kind of gives me an idea of the range of the values. I can see what I might, over here is a little bit smaller, but, we might be seeing something like an average of 10-ish for the percentage. Not super great, but ultimately, when it comes to a model, it's, a question of how accurate can I get it and how accurate does it need to be? What are the alternatives? These are things we always have to ask ourselves. So the mean is a little bit less than 10. And then let's see what the standard deviation is. All right, so 7.7. All right, so that gives me a good idea of how well my model will perform. Now remember, leave one out cross-validation is computationally intensive. If I want to do it, I need to do it really when I have fewer observations and a model structure that is faster to fit. If I'm going to do linear regression, there is like regular old vanilla multiple linear regression. There is a special formula that will spit it out for us, so I don't really need to worry about it. And if this is how I choose to conduct this. All right, this is all I've got. I hope you're doing well. Let me know if you need help with anything. Take care and goodbye.